In the silent, unending expanse of the cosmos, darkness is the rule. Light is the exception, a fleeting messenger from a violent past. For all of recorded history, humanity has stared into that abyss. We have charted the pinpricks of light, named them after gods and heroes. We have wondered in our poetry, our philosophy, and our science if anyone or anything is staring back. The question is, as old as consciousness itself, are we alone? Is this intricate, chaotic, beautiful dance of life unique to our small blue world, or is the universe seeded with the same potential, a cosmic garden waiting to bloom for millennia? The question remained purely a matter of faith and speculation. We had no tools to seek an answer, only the limited reach of our own eyes. The celestial ocean was vast, and our vessel was anchored to the shore. But now, a new eye has opened. An eye of gold and beryllium, 1,000,000 miles from Earth, cooled to near absolute zero. It is the most complex instrument ever built by human hands. A time machine designed not to look back at our own history, but at cosmic dawn. The James Webb Space Telescope was engineered to see the unseen. It was constructed to perceive the faint, stretched-out light from the universe's infancy. Yet, in its quest for the first galaxies, it has stumbled upon something far more intimate. Something that echoes in our own biology, in the very carbon of our cells. Far beyond the familiar spiral of our Milky Way, in a galaxy we have never visited. A place so distant its light has traveled for hundreds of millions of years to reach us. JWST has detected the unmistakable chemical fingerprints of the ingredients for life. This is not the discovery of alien beings, not yet. It is something more fundamental and perhaps more profound. It is the revelation that the universe is not sterile and empty, punctuated by one lucky planet. Instead, it confirms that the very same molecules that led to us are being forged in the stellar nurseries of other galaxies. The building blocks are not unique, the recipe is not local. The potential for existence, it seems, is a universal constant. To understand the magnitude of this finding, we must first journey back in time. Not to the dawn of the universe, but to the dawn of our own quest for knowledge. For centuries, the prevailing view championed by Aristotle and the Church was of a perfect, unchanging heavens. Earth was special, the center of all creation, and the stars were ethereal lights in a celestial sphere. This geocentric comfort was shattered by individuals like Copernicus, Galileo, and Kepler. Their meticulous observations revealed a universe of unimaginable scale and complexity. Earth was demoted from the center to a mere planet, one among many orbiting a very average star. With this newfound humility came a grander vision. If our sun was a star and the stars were other suns, might they not also have planets? And might those planets in turn harbor their own forms of existence? This idea, once deemed heresy, became the driving force of modern astronomy. We built larger and larger telescopes, magnificent cathedrals of glass and steel. Perched on remote mountaintops, they drank in the faint light from distant worlds. We learned of galaxies, immense islands of stars, separated by unfathomable voids. Our own Milky Way, once thought to be the entirety of creation, was just one of billions. The Hubble Space Telescope, launched in 1990, revolutionized our perspective once more. Floating above the distorting haze of Earth's atmosphere, it gave us a crystal-clear view. It showed us the pillars of creation, vast clouds of gas and dust where new stars are born. It captured images of galaxies colliding, a celestial ballet of gravitational forces. Hubble peered deep into the past, showing us galaxies as they were billions of years ago. But Hubble, for all its power, has a limitation. It sees primarily invisible and ultraviolet light. It is like a mariner trying to see the ocean floor using only the sunlight that penetrates the surface. Much of the universe's most vital activity is hidden, shrouded in impenetrable dust. Imagine a bustling city at night filled with lights and activity. Hubble is like a camera that can only capture the bright streetlights and illuminated windows. It sees the brilliant, obvious sources of energy, but it cannot see the warmth of the buildings, the heat signatures of life inside. It cannot perceive the activity happening behind closed doors or down dark alleyways. The cosmic equivalent of these hidden places are the dense molecular clouds. These are the stellar nurseries, the cosmic wombs where stars and planets are formed. They are opaque to visible light black smudges against the starry background. Inside these clouds, however, the universe is at its busiest. Gas is collapsing, temperatures are rising, and complex chemistry is unfolding. This is where the story of life's ingredients begins. To see inside, we needed a different kind of vision. We needed to see in the infrared. Infrared light is essentially heat radiation. It's the light that your television remote uses, the glow a warm object emits. Crucially, infrared light has a longer wavelength than visible light. This property allows it to pass through dust clouds that would block shorter wavelengths. It is the key that unlocks the secrets of the universe's hidden nurseries. The vision for a great infrared observatory in space began even before Hubble was launched. Scientists knew that to answer the biggest questions about the first stars, the first galaxies, and the origins of planets, we would need this capability. The project that would become the James Webb Space Telescope was born from this necessity. What followed was one of the most ambitious engineering challenges in human history, a saga spanning more than 2 decades involving thousands of scientists and engineers. The telescope's primary mirror had to be enormous to collect enough faint light. At 6.5 meters across, it was too big to fit in any existing rocket. The solution was an audacious piece of engineering origami, 18 hexagonal segments of gold-coated beryllium that would launch folded up. Then once in space, they would unfold and align themselves with nanometer precision. A single misstep, a single actuator failing would have doomed the entire mission. Furthermore, to see the faint infrared glow of the early universe, the telescope itself must be incredibly cold. Any heat from its own instruments would blind it, like trying to take a photo of a candle with the camera's flash turned on. Webb needed to operate at a staggering -233 degrees Celsius, just 40 degrees above absolute zero. To achieve this, it required a sunshield the size of a tennis court. 5 layers of a gossamer-thin material called Captain, each layer as thin as a human hair. This shield would block the heat from the sun, earth, and moon, allowing the telescope to cool to its operating temperature. Like the mirror, this fragile shield had to be folded, launched, and then meticulously tensioned in the vacuum of space. Over 300 single points of failure existed in the deployment sequence alone. The entire world held its breath as each step was painstakingly executed 1,000,000 miles from any helping hand. On Christmas Day 2021, the observatory began its journey, and after months of travel, unfolding, and calibration, it opened its golden eye. The first images returned to Earth were breathtaking, exceeding all expectations. Familiar celestial objects were rendered with astonishing new detail and clarity. But Webb's true power lay in its ability to perform spectroscopy. This is the science of breaking light down into its constituent colors, its spectrum. It is the single most powerful tool astronomers have for understanding the universe. Think of it like listening to a grand symphony orchestra from a great distance. To the naked ear, you might just hear a single beautiful sound. But with a sophisticated microphone and audio analyzer, you could isolate each instrument. You could distinguish the mournful cry of the cello from the triumphant blast of the trumpet. You could identify the precise notes being played by the violins and the woodwinds. Spectroscopy does this for light. Every element, every molecule in the universe absorbs and emits light at specific unique frequencies. These frequencies appear as dark or bright lines in a spectrum, a chemical barcode. By analyzing the spectrum of a distant star or galaxy, we can determine its composition. We can know with certainty what it is made of from billions of light years away. Webb's instruments are the most sensitive spectrographs ever sent into space, and they were trained on a region known as the Orion Nebula, a familiar, vibrant stellar nursery within our own Milky Way galaxy. The data confirmed the presence of a rich brew of complex molecules, carbon-based compounds, the very foundation of life as we know it. This was expected, validating theories about astrochemistry we've held for decades. But the real test, the true leap into the unknown, was to look further afield, to point this magnificent instrument at a cradle of stars in an entirely different galaxy, a place called SPT 041847, a young, dusty, star-forming galaxy. Its light has been traveling towards us for over 12 billion years. We are seeing it as it was when the universe was less than 2 billion years old. The light from this distant galaxy is impossibly faint, but through a quirk of cosmic geometry, its image is magnified by a gravitational lens. A massive galaxy cluster sits between us and SPT 041847. Its immense gravity warps spacetime, acting like a natural telescope. It bends and magnifies the light from the more distant source, making it visible to Webb. Even with this cosmic assistance, the observation was a monumental challenge. The team of scientists had to painstakingly collect the photons arriving from this ancient system. They let the light build up hour after hour on Webb's sensitive detectors. Then they began the arduous process of analyzing its spectrum. The search was on for the telltale barcodes of specific complex molecules. In the control room, the atmosphere would have been thick with anticipation. Generations of theory, decades of engineering, billions of dollars, all leading to this moment. The data streamed down from space, a torrent of numbers to be decoded. As the spectrum slowly took shape on their screens, the lines began to appear. Faint absorption features, tiny dips in the light at very specific infrared frequencies. They were looking for the signatures of polycyclic aromatic hydrocarbons, or PAHs. These are large, stable molecules made of carbon and hydrogen atoms fused into rings. On Earth, they are found in soot and tar products of incomplete combustion. In space, astronomers believe they are crucial stepping stones for more complex chemistry. They act like catalysts, providing a surface on which other atoms can meet and bond. They are like the foundational chassis upon which the machinery of life can be assembled. Imagine trying to build an intricate model car, but all your pieces are floating randomly in a vast room. It would be nearly impossible for the correct pieces to find each other and connect. Now imagine someone introduces large, flat magnetic boards into the room. The smaller pieces are drawn to these boards, and once there, they are much closer together. They can now easily link up to form more complex structures like engines and wheels. PAHs are theorized to serve as these cosmic magnetic boards. They gather simpler atoms and molecules, facilitating the creation of the more complex organic compounds needed for biology. Finding them within our own galaxy was one thing. It proved that the local conditions were right for this prebiotic chemistry, but finding them in a distant, ancient galaxy would be a paradigm shift. It would mean that the conditions, the raw materials, the very first steps on the road to life were not a local fluke. And then the confirmation came. The spectral lines matched perfectly with the known signatures of PAHs. They were there, unambiguously present in a galaxy from the universe's youth. For the first time, humanity had detected the specific complex organic ingredients for life outside the confines of the Milky Way. The silence in the control room must have given way to a wave of quiet, profound elation. This was not just another data point. It was a fundamental shift in our cosmic perspective. The discovery tells us that the universe was seeded with the potential for life from a very early age. The processes that we thought might be special to our own galactic environment are in fact commonplace. The great cosmic factory for producing life's precursors was open for business across the universe almost from the very beginning. Let us pause to fully absorb the implications. For so long, the search for extraterrestrial life has been tinged with a sense of improbability. The sequence of events that led to life on Earth seemed so specific, so contingent. We needed a stable, long-lived star. We needed a rocky planet in the habitable zone where liquid water could exist. We needed that planet to have a protective magnetic field and a stable atmosphere. And crucially, we needed a supply of the right chemical ingredients. This last point was always a major unknown. Perhaps the specific chemistry of our solar nebula was a lucky accident. Perhaps other star systems were chemically barren, devoid of the necessary carbon compounds. This discovery by Webb powerfully refutes that idea. It demonstrates that the very same complex molecules are present in environments vastly different from our own. SPT 041847 is a starburst galaxy, a far more violent and chaotic place than the modern Milky Way. Stars are forming there at a ferocious rate, bathing the entire galaxy in intense radiation. And yet, even in this turbulent environment, the delicate chemistry of life's precursors is thriving. The process is not fragile, it is robust. It is not rare, it is universal. The universe, it turns out, is not just passively allowing for the possibility of life, it is actively cooking up the necessary ingredients on a galactic scale. This finding deepens our understanding of a theory known as panspermia. The idea, in its various forms, suggests that life, or its building blocks, can be distributed throughout the universe. Early proponents like Fred Hoyle were often met with skepticism. But evidence has been mounting. We have found amino acids, the building blocks of proteins inside meteorites that have crashed to Earth. This proved that complex organic molecules could form in the harsh environment of space and survive a fiery descent to a planet's surface. The Rosetta mission to Comet 67P found not only water but also the amino acid glycine. This confirmed that comets, these dirty snowballs from the outer solar system, are delivery vehicles for life's essential materials. Now, Webb has expanded this picture beyond our solar system, beyond our galaxy. It has shown us the factory where these components are being mass-produced. Think of it as a cosmic Lego set. For the longest time, we thought we might have the only box of bricks in the universe. We looked at the incredible structures we had built with them, from bacteria to blue whales, and assumed our set was unique. Then we started finding loose bricks in our own backyard inside meteorites. This suggested that maybe other boxes of Legos existed within our solar system. Now with Webb, we have peered into a distant neighbor's house and seen through the window. And we have realized they have the exact same Lego set. The same colors, the same shapes, the same pieces. They may not have assembled them into the same creations as us. They may have built something entirely different, or they may have left the pieces in the box. But the fundamental potential is there. The same creative possibility exists everywhere we look. So where does this leave us in our search for an answer to the ultimate question? If the ingredients are ubiquitous, why is the universe so quiet? This is the heart of the famous Fermi paradox. If the universe is teeming with potential life, where is everybody? Webb's discovery makes this paradox even more acute. It closes one door on the idea that Earth is special. the one that suggested the chemical ingredients were rare. This forces us to look more closely at the other doors, the other potential great filters. A great filter is a hypothetical barrier that is so difficult to overcome that it prevents life from becoming an interstellar civilization. Perhaps the jump from complex chemistry to self-replicating life is the filter. Maybe the universe is filled with oceans of rich organic soup, but the spark of life itself is an exceedingly rare event. Or perhaps the filter lies further down the evolutionary path. The transition from simple microbial life to complex multicellular organisms like plants and animals could be the hurdle. After all, for billions of years, Earth was inhabited solely by single-celled life. Complex life is a relatively recent and perhaps improbable innovation. Another possibility is that the development of intelligence and technology is the filter. Countless species have thrived on Earth without ever needing to build a radio telescope. Intelligence like ours might be a bizarre evolutionary fluke, or in a more somber reflection, perhaps the filter lies ahead of us. Perhaps technological civilizations invariably destroy themselves before they can make their presence known on a galactic scale. Climate change, nuclear war, resource depletion, these may be the universal challenges that weed out nascent interstellar species. Webb cannot answer these questions directly, but it provides the crucial first step. It validates the foundation upon which the entire search is built, and it charts the course for the next generation of inquiry. The next phase will be to turn Webb's powerful spectrographs not just to distant galaxies, but to individual nearby exoplanets. We have already identified thousands of planets orbiting other stars. Many of them are in their star's habitable zone. The goal now is to analyze the light that passes through their atmospheres. We will be looking for biosignatures, chemical imbalances that could only be produced by living processes. An atmosphere rich in oxygen, for example, would be a tantalizing clue, as oxygen is highly reactive and needs to be constantly replenished on Earth by photosynthesis. The presence of methane alongside oxygen would be even more compelling. Finding these gases in the atmosphere of a rocky Earth-sized planet would be the closest we could get to confirming life without actually going there. This latest discovery of extragalactic organic molecules gives us renewed hope that such biosignatures are out there waiting to be found. It tells us that the planets we are examining are not forming in sterile environments. They are being born from the same rich, organic-laden clouds that we now see across the universe. They are being bombarded by the same comets and asteroids, delivering the same chemical payloads. The starting conditions are not the exception, they are the rule. This realization fundamentally changes our relationship with the cosmos. It recasts the universe from a cold, desolate, and indifferent void into a place of immense and shared potential. The story of life may not be a uniquely terrestrial one. It might be a cosmic narrative playing out in countless variations on innumerable worlds. The carbon in our bones, the nitrogen in our DNA, were all forged in the heart of a dying star billions of years ago. We have long known that we are made of stardust. Now we know that the stardust is the same everywhere. The same atoms, the same molecules, the same fundamental building blocks that make up our bodies are swirling in the nebulae of galaxies we can barely see. There is a strange and beautiful sense of connection in this. We are not cosmic orphans adrift in an empty sea. We are a product of a universal process. The physical laws that govern a distant galaxy are the same laws that govern our own bodies. The chemical processes unfolding there mirror the processes that once unfolded on a young Earth. We are in a very real sense kin to the cosmos. Our existence is not a miracle that happened in defiance of the universe's tendencies. it is an expression of them. The journey ahead is long, the distances are vast, and the challenges are immense. We may never find definitive proof of life beyond Earth in our lifetimes, but the search will continue, fueled by discoveries like this one. The James Webb Space Telescope is more than just a machine of science. It is a vessel for human curiosity, a monument to our relentless desire to understand our origins and our place in the grand scheme. It is an extension of our senses, allowing us to see what was once unimaginable. And as it continues its silent vigil 1,000,000 miles from home, it will keep gathering the faint, ancient light. It will continue to read the chemical stories written in the spectra of distant worlds. Each new piece of data, each new revelation will bring us closer to an answer. We look out into the great darkness, no longer just with a sense of wonder, but with a new sense of expectation. The ingredients are there. The ovens are on. Across billions of galaxies and trillions of planets, the cosmic kitchen is open. And for the first time, we have concrete evidence that our universe is not just a collection of sterile rocks and gas. It is a living, breathing, evolving entity pregnant with the same possibility that once sparked into consciousness on our own small, precious world. The great silence remains, but today it feels a little less empty. And the question, "Are we alone?" is infused with a thrilling new sense of hope. The universe is far from finished with its secrets, and our quest to uncover them has only just begun.